Hello, and welcome to Operations with Matrices. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This lecture is for Math 1508 Pre-Calculus at UTEP. Chapter 8, Matrices and Determinants, comes to us from Larson's 10th edition Pre-Calculus text. Section 8.2, Operations with Matrices. So, first of all, a matrix can be denoted by an uppercase letter such as A. We can refer to it as a representative element, Aij, just some kind of matrix. Or we can denote it as a rectangular array of numbers. And with anything we have in math, once we learn a new thing, right, whether it's real numbers, complex numbers, functions, let's go back elementary school, fractions, mixed numbers, all of it, right? We can add, we can subtract, we can multiply, we can divide. Right? So we want to find out what operations we can do with matrices, our newest thing that we can use in math. So, first of all, two matrices are equal if their corresponding entries are equal. For example, if I say these two matrices are equal, then row 1, column 1, -5 and -5. Row 1, column 2, x has to equal 13, or else these two are not equal. Row 2, column 1, y must equal 12. Row 2, column 2, they're both 8. So it must be that x equals 13 and y equals 12 for these two matrices to be equal, because their corresponding entries have to be equal. Another example. 16 matches with 16, 4 matches with 4, 5 must equal 2x plus 1. So that's row 1, column 3. If 5 equals 2x plus 1, we'll subtract 1. 4 equals 2x, divide by 2, x must be 2. Negative 3's, 13, 15, everything's good in row 2. 0, 2. But now in row 3, column 3, 4x equals 3y minus 2. Well, we already discovered that x equals 2, so 4x must be 8. If 8 equals 3y minus 5, I can add 5 and get 13. Divide by 3, and y will be 13/3. So we could use found information from a previous step in order to solve for another variable. Matrix addition. Now, bear with me. When you see the definitions, as in a lot of math, it looks like it might be hard, but once we go to the example, you'll see that it's what you would want it to be if you had to make up this operation. So matrix addition, if A is a matrix and B is a matrix with entries little a and little b respectively, both of the same order, m by n, then their sum is the m by n matrix given by A plus B equals Aij plus Bij. Now, the sum of two matrices of different orders is undefined, so they have to be the same size because we're going to add the components entry-wise. Right? Corresponding components get added. We also have a thing called scalar multiplication, and this is probably the first time you've heard the word scalar or used the word scalar, but think of it as scaling, right? A scale model. You don't want to rebuild the Empire State Building in your living room, although that'd be kind of cool. Big living room. So you'll build a scale model, so you'll shrink things down. We can also scale them up. So that's all a scalar does, is just a multiple of our matrix. If A, which is equal to the matrix Aij, is an m by n matrix, and C is a scalar, so any scale factor, the scalar multiple of A by C is still an m by n matrix. We say it's Ca, but that is C multiplied by each entry. Now, like I said, definition sometimes makes it look like it's going to be hard, but we write these for in general. Let's look at some specific examples. So, now for our given matrices, we're going to find A plus B and A minus B on this page. On the next page, we're going to find 3A and 3A minus 2B. So we'll get some work with addition and subtraction, and then we'll work with scalars along with some subtraction. So let's take two matrices. A is the matrix 1, -1. Second row, 2, -1. And B is the matrix 4, 10. Second row, -3, 7. So they're both 2 by 2. They each have 2 rows, 2 columns. Everything's good. To add, I am going to take row 1, column 1, and add to row 1, column 1, and that's my answer in row 1, column 1. I'm going to take row 1, column 2, add it to row 1, column 2, and put my answer in row 1, column 2. I'm going to take row 2, column 1, add it to row 2, column 1. My answer goes in row 2, column 1. And finally, the last one, row 2, column 2 plus row 2, column 2 gives me my answer in row 2, column 2. That's it. We add them component-wise. Don't make it any more challenging than that. There's plenty of things in math that are difficult. Don't let this be one of them. So you can see here that if I had an extra row in A, there would be nothing to add to it in B. So they have to be the same size because we add component-wise. In A minus B, we're going to do the same thing, only we're going to take 1 minus 4, negative 1 minus 10, 2 minus a negative 3, and negative 1 minus 7, simplifying to get our final answers. Alright, now, that was the definition of matrix addition. Let's look at scalar multiplication. If I want something like 3A, that's 3 times the matrix given by A, so that's first row 1, negative 1, second row 2, negative 1. I'm going to multiply 3 times 1, 3 times negative 1, 3 times 2, 3 times negative 1, in order to get my new matrix. So multiply each entry by 3, and I have my scalar multiple. When doing a sum or difference of scalar multiples of matrices, I did a couple of different ways in class, and a student brought up, hey, could you just do this? And I thought, that's genius. I'm going to put that in the video. So shout out to a student's name I forget because I don't even remember which class it was, but I appreciate the input. So in row 1, column 1, that's where my answer is going to be. I take my matrix A, entry 1, multiply it by 3, and then I subtract 2 times the row 1, column 1 entry in B. So 3 times 1 minus 2 times 4. 3 times negative 1 minus 2 times 10. 3 times 2 minus 2 times negative 3. And 3 times negative 1 minus 2 times 7. And in this way, you don't have to write out the 3 times A, and then write out 2 times B, and then find the subtraction. You can just use the formula for each entry. Been teaching this class for many, many years, and I love it when I still learn from my students, so thank you. 2 more matrices. We have a 3 by 2 and a 3 by 2. They're the same size, so I can add them. I add a row 1. 1 plus 8 gives me 9. 6 plus a negative 3 gives me 3. In row 2, negative 1 plus 4 gives me 3. Negative 5 plus 2 gives me 3. In row 3, 1 plus a negative 11 gives me negative 10. 10 plus 7 gives me 17. And I'm not really going to talk through it, but subtracting these values, you could check my arithmetic, see if you can find anything wrong. It happens. I'm human. But in the same way, we'll find the difference between the 2 matrices. Same A and B is on the last slide. 3A, I just multiply each entry of A by 3. 3A minus 2B, I was too lazy to write it out. That's not too lazy, a little bit too lazy. But also that was going to take huge amount of room on this particular slide. So let's just put here, ... as in the pattern continues. So 3 times 1 minus 2 times 8, that's 3 minus 16, which is negative 13. 3 times 6 minus 2 times negative 3, that's 18. Plus 6, which is 24. 3 times negative 1 minus 2 times 4. 3 times negative 5 minus 2 times 2. 3 times 1 minus 2 times negative 11. 3 times 10 minus 2 times 7. And we can find these values, and I encourage you to actually do this work. The ... This, there's this old joke that a miracle occurs. ... A miracle occurs, and this is our answer. Make sure you can perform that miracle. Make sure you can fill in all of these values to take us from 3A minus 2B to the solution that we're getting. Didn't want to type it. Alright, so now, example 3. A is a 2 by 2 matrix, and B is a 3 by 2 matrix. So there's nothing to add to the 5 and the 0. There's no way to subtract, because they're not the same size. As the dimensions are not the same, you cannot find the sum, the difference, or the difference involving scalar multiples. So any combination of A and B in addition or subtraction, you can't do it. But we can find the scalar multiple 3a. Let's multiply each entry by 3. 3, 6, 9, 12. And there we go. But not only can we add and subtract, we can multiply matrices. And multiplication of matrices is actually fairly straightforward when you see it, but don't let the definition mess you up. So, if A, which equals the matrix Aij, is an M by N matrix, and I'm going to write right here, M by N matrix, and B is an N by P matrix, the product, first of all, these two have to match up. This tells us it's okay to multiply. And our product, AB, is an M by P matrix. So our result in multiplication will be the number of rows from A and the number of columns from B. So writing down the dimensions helps us to see, is it okay to multiply? All right. And now what is the size of my resulting matrix? Well, okay, I know what size it is, but how do I get the entries? Well, the product AB is equal to the matrix Cij, where Cij is AI1 times B1j plus AI2 B2j and so on. What the heck? First of all, improper use of the m's. Those should be n's. Those should definitely be n's. But this looks hard. It's not hard. Don't let it be hard. I can't believe I wrote an M there. That should be an N. Not an H, an N. Basically, what it comes down to is we take the rows of A, and the columns of B, and we multiply, adding the values as we go. Let's look at examples. Alright, first of all, we're going to determine if we can find AB. If so, we're going to find the order of the result and the product. So matrix A in blue. So all of our entries from A are going to be in blue. All of our entries from B are going to be in green. We have a 3 by 3 matrix A. And B is a 3 by 2 matrix. Notice the 3 is in between. That means we're okay to multiply. Outside, 3 and 2 tells me my result is a 3 by 2 matrix. Now, this is what that whole multiply A's times B's and add as you go means. In row 1 of the answer, right, so we're going to have 3 rows, 2 columns. Row 1, column 1, the answer. So it's going to be 0 times 2 minus 1 times negative 3 plus 0 times 1. I'm multiplying the top row of A times the first column of B. Entry-wise, 0 times 2, negative 1 times negative 3, 0 times 1. Adding as we go. Unless it's a negative 1, then I subtract instead. Moving over here, this answer is going in row 1, column 2. So I'm going to use row 1 from A and column 2 from B. So I'll have 0 times 1 minus 1 times 4 plus 0 times 6. And even with zeros, I write it down so I can see. Look, in blue, I have 0, negative 1, 0. That's my row 1. 0, negative 1, 0. My row 1. Now, moving, row 2, column 1. So it comes from row 2 of A, column 1 of B. My answer goes in row 2, column 1. 4 times 2 plus 0 times negative 3 plus 2 times 1. Row 3, 8, negative 1, 7, column 1. So 8 times 2 minus 1 times negative 3 plus 7 times 1. So you can go back, especially with these in colors, you can see that row 1 of matrix A is 0, negative 1, 0, because that's the blue values in both columns. Row 2 of A is 4, 0, 2, 4, 0, 2. Row 3 of A, 8, negative 1, 7, 8, negative 1, 7. And then going back, you can reconstruct B. Look, the first column, right, the answer's in the first column from B, 2, negative 3, 1, 2, negative 3, 1, 2, negative 3, 1, 2, negative 3, 1, the first column of B. 1, 4, 6, 1, 4, 6, 1, 4, 6. Order matters. 1, 4, 6 is my column. We always read left to right, top to bottom. So left goes to top, right is going to be at the bottom. And then do all your little arithmetics. 0 plus 3 plus 0 gives me 3, and so on. Values added along the way. Hit pause, make sure you get the same answer. I just don't want to talk you all the way through it and make this video even longer. Alright, for some reason I decided not to use colors here, so let's go to a highlighter. Determine if you can find AB. If so, state the order of the result and find the product. So A is 3 by 2 and B is 2 by 2. Notice the 2's in the middle match up, and the result on the outside will have 3 by 2. So I take row 1 of A, and what I actually do is I type this, or as I write it in class, or write it as I'm making solutions for my exams, is I actually write -1, open parentheses, close parentheses, plus 6, and then the parentheses. And then I'll go, because I know there are 2 columns, I will put in my next, -1, parentheses, plus 6 parentheses. And then I'll fill in my columns. 2, and then 0. 2, and then 0. 2, and then 0. And I do all of my rows first, and then I'll do all of my columns and fill in the parentheses. It just makes it easier for me. I know that I have a 3 by 2. So I'm going to use all 3 rows of A. I'm going to put them into 2 columns. So the first row, -1 parentheses plus 6 parentheses. Second column, -1 parentheses plus 6 parentheses. Row 2 is -4 and 5. So -4 parentheses plus 5 parentheses. -4 parentheses plus 5 parentheses. I know to do it twice because that's my result. Row 3, 0, 3. 0 parentheses plus 3 parentheses. 0 parentheses plus 3 parentheses. And then I could come back in and fill in my columns. 2, 0. So in the first column, in my parentheses, I'll have 2, 0, 2, 0, 2, 0. Second column, 3, 9. I know in my second column of my result, I'll have a 3, 9, 3, 9, 3, 9 inside the parentheses. This is the step we'll want to see. If it says show your work, that's what we want to see right here. But also give us the solution. Do the arithmetic. Literally arithmetic. You can handle it. Fill in the values. You should be good to go. Alright. Same instructions. A is 2 rows, 1 column. B, 1 row, 4 columns. 1 and 1 in the middle tell us we can multiply. They match up. 2 by 4 is the result. So tiny little matrices will give us a large answer. What's row 1? 10. So it's 10 parentheses, 10 parentheses, 10 parentheses, 10 parentheses, 4 times. Because I know I have 4 columns. Second row, 12 parentheses, 12 parentheses, 12 parentheses, 12 parentheses. And then I fill in the column values. Column 1, 6s. Column 2, -2s. Column 3, 1s. Column 3, 3s. Feel free to check my arithmetic. Make sure this is the right answer. Pause button is all you need. Okay, so if possible, find AB, BA, and A squared. 2 by 2 and a 2 by 2, which is fantastic news because it's all 2's. So we know the 2's match up in the middle. We can multiply. The 2's on the outside tell me I'm going to have a 2 by 2 result. Rows of the first one. So rows of A, 6 and 2, in 2 columns. Row 2, 3 and -2. 3 and -2 in 2 columns. And then I'll fill in the columns of B, 0, 4. So 0, 4 in the parentheses of the first column. 1, 5 in the parentheses of the second column. Do the little arithmetics to get our answer. 8, 16 for the first row. -8, -7 for the second row. But now we want to multiply B times A. Now B times A takes the rows of B and the columns of A. So row 1 will be 0, 1. So 0 parentheses plus 1 parentheses. 0 parentheses plus 1 parentheses. Again, we know it's a 2 by 2 result, so we're good to go. Second row is 4 and 5. 4 parentheses plus 5 parentheses. 4 parentheses plus 5 parentheses. Rows of B, right? B times A, it's always rows and then columns, just like our dimension. Rows and then columns. So we'll take the columns of A. 6, 3, my first column, 6 and 3. 2, -2, my second column, 2, -2. Remember, order matters. Always left to right, top to bottom. Do your little arithmetics, and you'll have your solution. Don't forget that A squared is just A times A. Be very careful on this one, because you're going to take row 1, 6 and 2, 6 plus 2, 6 plus 2, and then column 1 is 6, 3, so fill in the 6, fill in the 3. Be very careful as you do these multiplications when you're using the same matrix, you're squaring it. It's just easy to get lost, and that's why I always write my rows first in as many columns as I need. rows first, and then I'll fill in my parentheses, my column values, just so I don't get lost as to where I am. A couple of properties of matrix multiplication. As we saw in the last slide, A times B is not necessarily the same as B times A. Sometimes it is, and that's fine. But it's not guaranteed to happen. In real numbers, if you multiply 3 times 4, you get 12. If you multiply 4 times 3, you get 12. All right? Either way, we call this the commutative property of multiplication, but there is no commutative property of multiplication of matrices. All right? In general, it's not going to happen. A times B, C, so associative property holds. A distributive property, as long as I keep A times B, A times C, the order correct. If I multiply by C on the right, I have to make sure I multiply it by on the right. Scalar multiplication is all good, associative property of scalars, but there's no commutative property. Make sure you pay attention to the order when you're asked to multiply. And finally, we need this concept of an identity matrix for some of the future stuff we're going to do. An identity matrix, first of all, is always square. The n by n matrix, n by n meaning the rows is equal to the number of columns, consists of 1s on the diagonal and 0s elsewhere. So it looks a lot like that reduced row echelon form that we talked about in section 8.1. If you need to, it's matrices with systems of equations. It looks a lot like the reduced row echelon form. This is called the identity matrix of order n, or n by n. It's always square, and we'll call it I sub 2 for a 2 by 2 identity matrix, I sub 3 for a 3 by 3 identity matrix, and so on. Alright, operations with matrices. Notice I didn't talk about division. We don't really have an operation of division. Instead, we multiply by the inverse. And if you want to know more about the inverse, you're just going to have to check out my next video. Thanks for listening. Appreciate it.